Welcome to Physics Master 10.
All right, welcome to The Explainer. Today, we're going to tackle a fundamental rule of the universe that is basically a cheat code for solving some really complex physics problems. So let's start with a classic problem. Say you want to figure out how fast this roller coaster is moving when it hits the very bottom. Now, if you try to solve this the old way, using kinematics, you're dealing with vectors, changing angles, shifting acceleration, honestly, it gets messy fast. There has to be a better way, right? Okay, so let's dive into this superpower. It's called the law of conservation of energy, and it's one of the most powerful and frankly beautiful concepts in all of physics. So the core idea here is actually super simple. You can't create energy out of thin air, and you can't make it disappear. All you can do is move it around or change its form. Think of it like a bank account for energy. The total amount never changes. Okay, so for most of the stuff we'll be looking at, things that are moving, we're talking about something called mechanical energy. And you can really just think of it as two big buckets. One bucket for the energy of motion, that's kinetic energy, and another for stored energy, which we call potential energy. Now let's start building our toolkit. And to really get a grip on this, we're going to start in a perfect world. You know, a place where all the annoying stuff like friction and air resistance just doesn't exist. And this simple-looking equation, this is our key. All it's saying is that in this perfect little universe, the total energy you start with, that's your kinetic plus your potential, is exactly the same as the total energy you have at the end. It's perfectly balanced. So let's jump back to a roller coaster. Right at the very top at point A, it's 30 meters high, but it's barely moving, right? It's starting from rest. That means its motion energy bucket is totally empty. But its position energy bucket, man, that thing is filled to the brim. It's all potential energy. And here's where the magic happens. We just set that initial potential energy, that mgh thing, equal to the final kinetic energy at the bottom, the 1/2 mv squared. As the car drops, all that potential energy gets converted into motion. And bam, with some pretty basic algebra, we can solve for the final speed. No crazy vectors, no headaches. Okay, but let's be real. The world isn't perfect. There's a villain in our story, and its name is friction. It's the thing that seems to make our energy just vanish. So when friction enters the picture, that neat balance of mechanical energy gets thrown off. Some of it gets turned into heat. But here's the cool part. Our main law, the conservation of energy, isn't actually broken. We just have to update our equation. We add this little term for the work done by non-conservative forces. Think of it as an expense line in our energy budget, accounting for every bit of energy lost to friction. Okay, so this is a kind of funny analogy from the source material, but it really works. It's comparing useful mechanical energy to a group of organized students and the wasted heat energy to, well, a group of disorganized hippies. The whole point is that heat is super disorganized random energy. It's all over the place. And that makes it way less useful for doing something focused, something mechanical, like pushing a car forward. Let's see how this works with a real example, like this skier. So you start with all the potential energy the skier has at the very top of the slope. Then you just subtract the energy that gets turned into heat because of friction on the way down. And whatever is left over, that has to be the kinetic energy at the bottom. It's really that simple. And this energy superpower, it's not just about gravity and height. See, potential energy isn't just about how high you are. You can store it in all kinds of ways, like squishing a spring or, stretching a rubber band. Take Hawkeye here. All that energy he puts into drawing his bow, that gets stored in the bowstring as what we call elastic potential energy. And the second he releases it, all of that stored potential energy instantly converts into the kinetic energy of the arrow. Whoosh! Same principle, different kind of storage. Okay, time for the boss battle, the ultimate test. Check this out. We've got a block that slides down a ramp, goes through this insane loop-the-loop, and then flies off another ramp. I mean, can you imagine trying to solve this with kinematics? It would be an absolute nightmare of changing forces, angles, everything. But here's the magic trick. Gravity is something we call a conservative force. Now, that's just a fancy way of saying that gravity doesn't care about the path you take. It only cares where you start and where you end. And because of that crazy complicated loop in the middle, it doesn't matter at all. We can literally just ignore it. All that matters is point A, the start, and point C, the end. And just like that, the whole problem becomes, well, beautiful and simple. All we have to do is say that the potential energy it started with, up at height h, has to equal the potential energy it has at point C plus the kinetic energy it has at point C. That's it. We can solve for the starting height without even breaking a sweat, and we never once had to think about that loop. So all of this brings us full circle, right back to our original question. When should you use this awesome energy cheat code versus the old school grind-it-out kinematics method? All right, let's put them head to head. Here's a super simple problem. A ball falls off a table. On the left, you've got the kinematics way with all its vectors and equations. On the right, the energy way. They both get you to the exact same answer, but come on, which one would you rather do on a test? So let's boil it all down. Here's the big takeaway. Energy methods should be your default, your go-to weapon. Why? Because they don't care about the messy path in the middle. And the math is way simpler. No vectors. There's really only one situation where you have to pull out the old kinematics tools, and that's when a problem asks you how long did it take. Because our energy equation, it doesn't know anything about time. And trust me, this whole principle is everywhere you look. Take your car, for example. The engine is only about 15% efficient. That means only 15% of the energy from the gasoline is actually used to move the car forward. And that kind of leaves us with one last big question. If energy is always conserved, if it can't be destroyed, but your car is only 15% efficient, where in the world does that other 85% of the energy from the gasoline go? It has to go somewhere, right? Something to think about.